during the what we call as during the video that I have told you to watch, okay, on the class, have we learned about the graphite furnace, AAS? Right, in AAS, we have discussed about graphite furnace in the video.
Yeah, in the video got AAS already.
I mean AAS, we have several type of AAS. Do we discuss about the graphite furnace? I just forgot. This is the flame AAS, right? So as being discussed, okay, and also have been asked in the quiz, what happened to the sample when it being sucked into the small tube and aspirate into the flame? What happened? So the fine aerosol is created and mixed with the fuel and oxidant and introduced into the flame so that the atomization happened. You remember the question in the quiz, right? And the metal atoms that absorb the light from the source, and then the detector will detect some loss of the radiation from the holocated lamp, okay, the radiation source. All right, so this is how the burner head looks like. All right, we have two types of oxidant fuel in the burning process in AAS, flame AAS. We have combination of air and acetylene. The temperature is about ranging about 2100 degree to 2400 degree of Celsius. And the second one, we have more, much hotter than the air acetylene, which is the nitrous oxide and acetylene, which is the temperature ranging about 2600 to 2800 degree of Celsius. Right, this is the example of the fuel and oxidant combination and what is the temperature. Normally we use air acetylene and nitrous oxide acetylene combination in the flame AAS. So this is atomization process. Just for revision a little bit. The process converting sample, solid or solution into vapor particles. Okay, why solid or solution? Normally AAS use solution sample, but some of AAS we can analyze solid sample, but not so much use in the labs. Okay, most of labs use the solution sample type of AAS. And when it turns into vapor particles, the individual molecules and individual gases atom will be atomized using atomizer. Okay, the process in the atomizer is converting the solution into aerosol, remove all solvent. Okay, then we can see that from solution turn into solid and vaporization happen from solid into gas and atomization of molecule into the individual gases atom. Okay, individual atom, so that the excitation state happen, okay, and the emission state is only measured for the AES instrument, not AAS, okay. And the ionization needs more high energy, but we don't need this ionization happen undesired, okay. We just need the excitation of the atom. When excite, and then this is where AAS measure the analyte. Okay, when the light source produce a radiation and excitation happen, the atoms absorb the energy and the detector will detect the loss of energy. Okay, And different for AES, this one is emission for AES. The measurement is not involve any about absorption of any energy, but just measuring the emission of energy after the excitation stage. So this emission of energy measured for AES instrument. Right, so this is for AES. Okay. All right. We also have the flameless atomizer, which is the graphite furnace AES. So we don't have any burner here. Sorry, we don't have any flame here, right? Oh, I forgot to start the class with prayer. Okay, so we can start again with everyone's own prayer. Okay, for the Muslim, we start with Al-Fatiha. Bismillahirrahmanirrahim. Alhamdulillahirabbil alamin. Maliki yaumiddin. Iyyaka na'budu wa iyyaka nasta'in. Ihdinas siratal mustaqim. All right. So we have also the graphite furnace AES, which is using the graphite tube with small tube. Okay, and the tube, the sample will be injected into the tube, a very small amount of sample, and the heating process will be happen inside the tube. Only a few sample, microliter samples placed in the tube, dried, ash, and then vaporized in high temperature. So the atomization happen only in the tube. It is more efficiency because it is not vaporized outside the system, okay, into the air, but happen in the tube. So that the measurement is also occur inside the tube, the absorption and so on. This is very excellent in sensitivity and low detection limit. So this is how the graphite furnace AES looks like. The tube will be put inside here. It is very small tube. Also can use HCl and EDL. It is normal for AES. But for graphite tube, we have special feature, which is the auto sampler. We don't need to put a sample one by one. We just put in the sample tray a small amount of sample, so that the reading process automatically done by the instrument. So we just put all the sample, set up the instrument, and go watching movies at the cinema also can. And then we come back, the result is there being analyzed. All right. Where's my mouse? Oh, right. This is a schematic diagram how the graphite furnace looks like. Okay, it's not AES. Sorry. Okay, this is AES. This is wrong. Yeah. So you can also fix in your notes. Okay, it's a little bit confusing. Okay, not AES, AES, okay? All right. This is just for revision. We have learned this in the video, right? I want to have a confirmation again. Guys, we have learned this in the video, right? Or not yet?
Not this part yet, Doctor.
Not this part yet, right? Okay, so we have to be clear in this part, right? So this is the graphite tube. Okay, the sample will be injected here, see, and then the heating process will be happen in this tube. So the instrument will heat the tube, surrounding the tube, small tube, right? And then the atomization happen inside the tube. The sample being atomized inside the tube. The hollow cathode lamp will produce radiation through the tube, okay? And the absorption happen inside here, right? So the detector will detect the loss of radiation after the light coming out from the tube, right? Then we have the signal, which is the absorption. Remember, I've told you during the last class, all the instruments are, I would like to hear the keyword. It's okay. All instruments are?
Not clever.
Not clever.
Yes.
Or stupid, right? All the instruments are not clever.
I was
need
gonna say calibrated.
Yes? Sparkly?
I was going to say calibrated.
All the instruments are not clever, not calibrated yet. After we calibrate, then the instrument know. So the one who teach the instrument on how to know the concentration of any analyte is who? Is us, right? The what we call as the user of the instrument. All right. So the instrument itself, they are not clever. They don't know about the concentration. They only know about the signal. Sparkly, understood? After we calibrate the instrument, what is calibrate? Okay. Well, calibrate is we run a known concentration, a series of known concentration of analyte, the targeted analyte. For example, zinc. We analyze 1 ppm of zinc, and then 2, and then 3, and then 4, and then 5. Minimum 5 concentration. And then the instrument, oh, this is 1 ppm. I know the signal. Oh, this is 1 ppm. We teach the instrument, right? And then until 5 ppm, so the calibration plot must be made, right? And then the instrument know already if the unknown sample being analyzed within the calibration plot, so the instrument will know what is the concentration. Okay, am I clear? Understand? Guys?
Yes,
Whoa.
Doctor.
All right. What is this coming out? Okay. All right. So there we have the graphite tube. Okay. We have the optical window, and then at the both side optical window, we have the hole here for the auto sampler to inject the sample inside the tube. All right. So the flame is replaced now by an electrically heated graphite tube. Okay. A few microliter sample placed in the tube, and it is dried, etched at lower heats, and vaporized at high temperature inside the tube. The atomization happen. Okay, and this is much efficient than flame because all the atomized analyte is inside the tube. Okay. So we have to program the instrument. Okay. The first one, the temperature will be ranging about 50 to 200. The RAM of temperature. This is for drying, and then the pyrolysis happen. Temperature between 200 to 800. Net atomization happen between 2000 to 3000 degrees of Celsius. Very high temperature, right? Their atomization will be happen inside the tube. Right? Inside the tube, there are a platform here to when the auto sampler will inject. Actually, there's a hole here. All right. The auto sampler will inject the sample inside the tube on the platform. All right. Very small amount of sample. So this is comparison, right? Small sample size compared to flame, large sample size, analyzed in a low concentration range, which is in part per billion rather than the flame in part per million, longer analysis time, and so on. Okay, you can read this as a comparison. But I want to ask a question to you. What you can say, you just predict which one, if you send the sample to be analyzed using graphite and flame, which one is much more expensive than, from each other, comparing to each other? Which one is expensive? The cost of analysis. Graphite furnace or flame?
Graphite.
Sparkly? Yes, of course, graphite furnace, right? The cost of the graphite tube itself is very expensive, right? The range of sample is in ppb range, all right? And then what else? Okay, the cost of electrical use to heat, right? Everything is much more expensive for the graphite furnace. Okay, this is a comparison between the all the instrument. Okay, in the term of detection limit. So we have learned until graphite furnace now. After this, we learn about ICP, MS, and so on. Right? This is the element. Okay, and then we can compare the detection limit. For example, we compare arsenic. Okay, flame is 150 part per billion, but for the AS 0.2, very small. ICP is 50. ICP-MS, okay, ICP-X03, ICP-MS much lower detection limit, which is 0.006 ppb. DRC ICP-MS, wow, this is superb, right? 0.0005 part per billion, right? So this is much more sensitive. Okay, we don't have this one in UTM. Okay, we only have the flame AS, graphite furnace AS, and also ICP-MS. Right, we don't have ICP radial and axial as well. All right, and then the next, okay, we have the Hydra generation AS. Okay, Hydra generation AS. Okay, the slide is wrongly put here, I think. All right, so a certain metalloid element from is a volatile, okay, covalent hydride. Can form volatile covalent hydride which can be separated from the main matrix. Right, meaning that not all elements can be detected successfully using flame and graphite furnace. Some elements are metalloids, which are much more volatile. If much more volatile, it can be vaporized, and then this just disappeared in a very high temperature. Okay, at 40 degrees, the element will be vaporized. So it is hard to manage using all these, instrument that dealing with heat, right? So to solve this problem, we have the hydride generation AS and also the cold vapor AS. Okay, the hydride generation is special for element, metalloid elements such as arsenic and selenium, which is very sensitive to heat. And of course, mercury is much more sensitive to heat. So we have a special instrument just for mercury, which is the cold vapor AS, right? So hydride generation and cold vapor both are not involved heating. Okay, we just react all the sample with the special chemicals, reagents, which can volatile. Okay, we can vaporize or volatile all the element, the targeted element which are more sensitive and can be detected without any heating, just in the chemical reaction. All right, this is hydride generation, advantage for some elements and also limitation for some elements. Okay, the cold vapor is only limited to mercury. Okay, volatile free atomic state to at room temperature only. So this is the problem of mercury, can volatile at room temperature. So the cold vapor will improve the sensitivity, okay, with 100% of the sample efficiency. And all the mercury in the sample solution placed in the reaction flask is chemically atomized, not through heating, but chemically atomized, not thermally atomized. It is chemically atomized and transported the sample cell for measurement. The concept is similar now. Okay, we have the holocated lamp, right? We have the detector to detect how much of the absorption. But now, as you can see, for all the AS, all type of AS, we have flame, graphite furnace, hydride generation for metalloids, also cold vapor for mercury. The difference are in the atomization stage, right? Can you see that? Right? You must understand that hydride generation AS, especially for metalloid, because it cannot be heated using graphite furnace or flame. Yes, it can be heated. It can be atomized by thermal, but not so. The limit of detection is not so good. Okay, so we need to use the instrument much more better. Extremely low detection limit. If we have small concentration in the sample, we cannot detect using flame and graphite furnace. For example, selenium or antimony or lead itself, right? But we can detect much more, efficiently using hydride generation, not involving any heating, right? So similar as cold vapor, AAS is only for mercury. because mercury is the most sensitive element to the heat. So the monochromator and also the photomultiplier concept are similar with the UV, right? And the standard methods, all right? Have you learned about the standard methods with Dr. Aida previously? Okay, let me repeat a little bit. Okay. To analyze any analytes, okay, in our sample, okay, we must refer to the standard method first, because we are not the first one who want to analyze the analyte inside the sample. For example, you want to analyze what? Mercury, or for example, this one. You want to analyze the nickel, vanadium, iron, and sodium in crude oils. You are not the first one. Previously, there have been any analysts, right, or chemists who already want to detect these elements, okay, or these analytes inside the crude oil sample, and come out with a very good method, with much more, which have done the method validation, okay, and the method have been verified. So they have registered the method, and when we follow the method, we will get the result much more accurate. Okay, have you understand that? Have you learned about the standard method? Please, someone. Guys, learn, right? So the standard method, the method that we need to refer, it is the method that have been verified, right? They have been standardized. There have been a method validation for that. So we just follow the standard method in any analysis that we want to do. If you want to analyze, for example, the nickel alloys, right? So we use this ASTM standard method, for example. We have a lot of standard method, ASTM, APHA, AOAC, and so on. But we need to choose. And then in our report, we need to mention that we follow these standard methods, ASTM E1835-14 for the analysis of nickel alloys whatsoever in your report, right? And then all the people will know that you have referred the standard method to do your analysis, right? If you do your own method, you need to verify why you do your own method. We call that as in-house method, meaning that you have altered the method with your own method, but you need to verify why. Maybe it's because you don't have any special apparatus as the standard method mentioned. Maybe your instrument is quite different, right? Maybe you have other situation that need to alter a little bit about the standard method. So you need to mention your in-house method, okay? The method that you or yourself done, not completely 100% similar to the standard method, right? Understood, guys? So we have, to summarize, here we have several types of AAS, okay? We have the flame, graphite furnace, cold vapor, and hydrogenation of AAS, right? And then we have the ICP OES. And then we have the ICP-MS for the spectroscopy, right? There are also interference that can cause, overlapping in the lights due to the radiation overlapping that of the light source. Okay, interference also can due to the background. Okay, the contaminants inside the sample, and we need to do the correction. How to do the correction? We have the alternative wavelength of the element of the HCl. Okay, hollow cathode lamp, the source of light. We have alternative. If the hollow cathode lamp that we use, the wavelength of the elements, okay, that we use is, for example, not 710. For example, for copper we have another one. For example, 650. If there are a lot of there's a lot of interference, so we change the HCl to another type of HCl with different wavelength for copper, so we can remove all the interference. Or for lead, we have two types of two wavelength of hollow cathode lamp that can be used, 283.3 or 217 nanometer. All right. We have background correction as well. which using the high energy deuterium background corrector. Right. Now we learn about another instrument, which is AES and ICP OES and ICP MS. Okay, what is the difference for all these instruments? The atomic emission spectroscopy, as I told you, that is not involve absorption, it is emission. The analyte being excited, right? And then from the excited state, it will come back to ground state and emit some energy. That energy being measured. So that is AES. Okay, what is ICP? ICP, we have ICP OES, ICP MS, right? So ICP, right, is the inductively coupled plasma. Okay. Now the sample are not being transformed into atoms like AES and AES, but transformed into plasma at much more higher temperature. And detection, we can have two type of detection using ICP. We have the optical emission spectroscopy, a spectrometer, and also we have the mass spectrometer, right? This is only I can just go very fast on this instrument, right? So for the theory, AES use measurement of the optical emission from the excited atoms to determine the analyte concentration, right? Because the analyte emit radiation when they revert to the back lower level from excited state to the ground state. What is the advantage of AES? All atoms in a sample are excited and detected simultaneously. So we can detect simultaneously, not one by one, right? But the disadvantage is the detection is only at high concentration, which is not in low detection limit. It is in high concentration. All right. We have AES, we have ICP AES, and we have ICP MS. Right. This is AES. Okay. The sample being aspirate and also burn like flame AES. We have a mirror here instead of like radiation source, right? Radiation source, no, we don't have it. We have a mirror here and the lens, okay, and the slit and the filter and photodetector. So when the atoms being excited and go back to the ground state, emit some energy, okay, and pass through the lens, okay, slit and filter and being detected by photodetector. So the difference is, what is the difference between AES and AES? The light source. AES don't have any light source, right? So now we learn about ICP OES. Okay, as I told you, now the sample is not, the analyte is not transformed into atom but into plasma. The atomization is into the plasma. And use optical and emit, right? Emission light. Also like AES, right? The ICP OES measure the emitted light from the analyte. What is plasma actually? It's a stream of highly ionized gas containing electrons and positive ions. It is electrically conductive and affected by a magnetic field. This is plasma. It is how it's being burned, okay? Preheating zone, induction zone, and then we have initial radiation zone, and this is a normal analytical zone. The blue light is plasma, right? What about the temperature to produce a plasma? Is between 6,000 Kelvin to 10,000 Kelvin, okay? Temperature. Intensity of light emitted is proportional to amount of element in the sample. So this is, it's for ICP OES. The theory is the emitted light, okay, proportional to the amount of element in the sample. So ICP is ideally suited to rapid multi-element analysis. What is the comparing ICP, OES, MS, okay, with the AES, AAS, right? we can detect multi-element at the same time. And also provide high sample throughput and wide calibration range, low background, low detection limit, and for many elements. This is process. Okay, the solution convert into solid, which is the solvation. Vaporization happen. Also atomization happen, but it is big. Furthermore, heated into ionization stage. Okay, plasma is the mix of, again, what is plasma? A stream of highly ionized gas. So the heating is continue after atomization into ionization. Right? That is different. Okay, it's just not stop at atomization. Continued with ionization. So this is instrumentation of ICP OES, RF generator, okay, to produce plasma. We have torch, then plasma has been produced. We have spectrometer to measure the emission of light, and we have the detector and computer. This is how the ICP OES looks like. Okay, schematic diagram, how the process happen, sample being transformed into plasma. We have also nebulizer, and then we have the transfer optics to detect the emission of light, and then also photon multiplier and also computer to analyze the result. So the function of nebulizer is converting the liquid into aerosol. We have nebulizer in ICP, in AES and AES, right? Converting liquid into aerosol that can be transported to the plasma in this case. Spray chamber to remove large droplets. What is the RF generator? The radio frequency generator provides power for the generation of plasma. Sustain the plasma discharge. This is the function of RF. Okay, sustain the plasma discharge, and ICP OES operate at the frequency of 27.12 and 40.68 megahertz. So for plasma, we need to have the RF, okay, the radio frequency generator, and we have the detector. Similar with UV, AES, right? We have PMT, photo multiplier. We have other type also, solid state detector, photodiode array, a charge injection device, and so on. But normally PMT. Application also a lot of wide application in the field of agriculture to analyze the soil, plant, fertilizer, right? So the glass industry, ceramics industry, because you can detect simultaneously many elements at the same time, all right? And also other field of study, geochemicals, pharmaceuticals, semiconductors, and so on. The advantage, multi-element, of course, a few chemical interference, excellent linear dynamic range, low detection limit, and also speed. Okay, now we move to ICP MS. The difference is MS, right? The plasma is similar for atomization, and then we have MS. What is MS? Right, the mass spectrometry from ion generated by ICP. The instrumentation is we have the plasma generation part similar with ICP OES, okay. And then the difference is we have the mass filter, the quadrupole, okay, and also ion detection system. Because we are not measuring emission of light here, we are measuring mass spectrometer. Okay, mass is a mass to charge ratio of the element. Okay, this is the ion source, similar, right? Ion beam focusing the ion extracted by the interface and send them into the quadrupole. Okay, we need to have the ion beam to focus all the extracted elements and send into the quadrupole. And then in the quadrupole, right, it separates one type of element, okay, from other element. Okay, meaning that all the elements being analyzed separately. Okay, referring to what? Okay, according to what the quadrupole manage all these the elements. Okay, based on one mass. Okay, m over z. Okay, mass to charge ratio to make it through at a time. Many masses enter, only one make it out. All right. So application also we have wide application of ICP-MS. The cost of analysis of ICP-MS is greater, which is expensive than ICP-OES because of the MS part. Okay, the mass spectrometer part, analyzing the mass to charge ratio of all the elements. The comparison between ICP-MS and ICP-OES. ICP-MS for most metals and non-metals, similar to ICP-OES, but the detection limit is much more lower, which is part per trillion, comparing to ICP-OES is part per billion to mid of part per million. Advantage are rapid for both and multi-element also for both, but for ICP-MS, wide dynamic range, good control of interference. The disadvantage, limited total dissolved solid tolerance for ICP-MS and complex interference and poor sensitivity for ICP-OES. Again, we have the comparison here, okay, for element and also instrument that we can use, right, based on the detection limit, right, can choose here. But again, it's also about the cost of analysis. If you have a lot of money, yes, every element you can analyze just using ICP-MS, right? So this is the different as comparison. As you can see, for AS we have the light source. For AES we don't have the light source. Okay, just measuring the emitted light from the sample that have been atomized from excited state to ground state. But for the AS, the absorption of energy for the atoms to be excited from ground state to excited state is being measured. A detector will detect the loss of energy from the radiation source. That is AS, that is AES different. But for MS, mass spectrometry, right, the measurement is in a mass to charge ratio for every element, right, not in kind of radiation absorption or emission, like both AS and AES. But for MS, it's based on mass to charge ratio. That's why it's much more expensive, right? So do you have any question about all the instrument? I will put the today's lecture video and also my previous video lecture also in the or you can just, guys, you just subscribe my YouTube so you can watch all the lecture about all the instruments, my previous lecture. Can you do that? My YouTube channel is Faizwan Abdullah. Okay, just subscribe.
Already done, Doctor.
Already done. Good. I'm not a YouTuber, but I put all the class lecture video inside there so that we can watch again, just to ease the student, right? I'm not a YouTuber, guys. Okay, all right. In the analysis in spectroscopy methods, we have to prepare the sample accordingly, right? We know that all instruments have different detection limit, okay, different type of we have, okay, as you can observe all instrument, we have two part, right? The atomization part and also the detection part. For example, flame AAS, the atomization part is flame and the detection part is AAS, atomic absorption. We have graphite furnace AS. The graphite furnace is the atomization part and the detection part is AS. ICP OES, the atomization part is ICP, which is not only atomized but transformed into plasma. And the detection is OES, optical emission spectroscopy. Okay, so we have two side names of the spectroscopy instrument. Okay, similar also with the chromatography instrument if you learn after this, okay, after the mid-sem. we have two part of instrument name, which is the first part will be in case of spectroscopy, the first part will be on the atomization. What is the method? Flame AAS. Flame is the atomization part. AAS the detection part. ICP MS. ICP is atomization. MS is the detection part. Right? So the critical point in the sample preparation is we have the sampling and sample pretreatment. We have learned this in the first chapter, right? We have the sampling process and sample pretreatment process, right? This is to avoid the contamination when preparing the sample, and we have the sample prep. Sample prep is to prepare the sample according to the instrument, right? And then we test preparation and test solution, okay? And then determination and calibration process, the last step. Okay, we analyze the sample. Okay, it begins with the sampling process. Sampling is the most crucial part in the analysis. If you done sampling with a wrong method, okay, you do some errors in sampling, so all the other part, all other section or other steps are not valid anymore. So sampling and sample pretreatment is the most crucial part. Okay, right, and then sample preparation basis is right, this conversion of a solid into liquid, right? If you have a solid sample, you need to transform into liquid because most of the instrument use liquid, right, as the sample to be analyzed. And the sample solution is a liquid form of the sample having the analytes is an ionic solvated form of observing that the analytes will pass through 0.3 micron, meaning that you need to filter the sample, okay? Not a cloudy sample with lot of rubbish inside there. We need to filter so that we have a clear sample, right? So that the instrument will not affected by the rubbish, all the suspended solid inside the sample. This is to take care of the instrument. We need to filter the instrument. And then, all right, as I told you, we need to prepare the standard solution. All the instruments are not so clever. We need to teach them. So we prepare a series of a non-concentration of the analytes, of the targeted analyte, right? Using the standard. Right? And then we do matrix matching, the ability to match the sample solution to the standard solution, such that all nebulizer and plasma related effects are eliminated or can be corrected. This is another step, okay, matrix matching. But the most important is the standard preparation. All right, sampling. You have done sampling, for example, then you do sample preparation. Okay, determine the amount, weight of volume, prepare, replicate sample for statistics, bring the analyte into the best chemical form. Okay, what is the purpose of sample preparation? You have the sample. Before you analyze, you need to prepare a little bit. Okay, make sure that all the sample, all the analyte, or the targeted analyte being separately or dissolved 100%. All right, and then you need to bring the sample, do some pre-concentration. Okay, we remove as much solvent as we can and concentrate the analyte, right? And eliminate interference. That is most important thing. Some sample you need to heat at certain temperature to remove all the organics interference, all right, that can affect the reading of the sample, right? And then that's why we need to refer the standard method. The standard method will tell us how to do the preparation. Need to heat at what temperature, how long, and so we need to mix with what type of chemical, acid, and so on. So just follow standard method. There's a reason why the standard method have told us to do that. Okay, because the research has been done previously to analyze the same analyte as you want to analyze. Okay, that is the best condition that they have found to analyze the analyte using the targeted instrument. This is sample pre-treatment. Grind and sieve to suitable size to obtain required homogeneous size. You have learned about cone and quarter method previously, right? Am I correct for the solid sample? If you have learned, give me thumbs up. Cone and quarter method, you have learned that? Yes, all right. Dry the sample, right? And sample preparation, dry etching. This is what I told you. Need to heat at certain temperature, mix with needs to oxidize. Okay. Wet digestion. What is mean by digestion? We put acid. Okay, this is acid treatment. Put acid and heat the sample. Fusion technique, heat with flux or acid until molten state. We have several types of sample preparation according to standard methods. Okay, for different analyte, different sample, we have different type of standard of sample preparation. All right, normally it involves heating and digesting, which is put acid and heat it to remove all the interference, organic matrix, and so on. Okay, why? Decomposition is required. Decomposition is what? The destruction of the organic matter inside the food sample, for example. To convert from solid into liquids, to destruct all the matrix, to separate the interfering substance, to isoformation of sample, homogenization, and so on. We have pros and cons, okay, of the digestion techniques. We have wet digestion, which is acid treatment. Put the acid. It is low cost, but may lose analyte by volatilization because we heat. Okay, using the wet digestion, we heat the sample that have been mixed with acids. Okay, analytically accurate, economically efficient, safe, and easy to perform the digestion. Right, to put acid and heat. And then this is much expensive than digestion method, which is put acid and heat like that. We have the microwave assisted digestion. We have this specified instrument for that. We put the sample inside, and the analyte will not volatile outside of the vial because it is closed and heating. It is being heated closed in closed vial using microwave heated. Okay. So we have three types of sample digestion technique. This is hot plate. You do it by yourself like this in the lab, or you have the special equipment, microwave assisted digestion, or you have block digester, which is using heat, electrical heating as the heating source to digest all the sample. This one is using microwave. Okay, so much more expensive. This one, microwave digester. For example, determination of cadmium in fish using the method AOAC 999.10, the closed digestion. Okay, with the fish, pipette, peroxide and acid mix into the sample, close the sample vial, and this is a block digester, right? So put in block digester, RAM a certain temperature for how many minutes, can then add ultra pure water to the mark. Again, we have determination of cadmium in wastewater method APHA 3030E, open digestion, just digest like that on the heater, right? Open digestion, cheap method. And then we have microwave digestion, expensive method. Fusion technique also as well. We have a fusion techniques, mix of excess of alkali metal salts known as flux, okay, in a crucible, heat with high temperature. Together in molten state. This is fusion techniques. We have a lot of techniques to prepare the sample. And some errors also happen sometimes. Incomplete dissolution of the analyte, loss of the analyte by volatilization, like we do open digestion, right? The analyte volatile outside of the conical flask, for example. Contamination from each of the solvent or the conical flask wall have some some contaminants on the wall, and then you just use it without washing it, so some interference will be there. And then we need to do the recovery. What is recovery? Okay, is a measure of the amount of analyte in the assay relative to the amount of analyte in the sample. Okay, you have a known concentration of you have spike. Okay, put a known concentration of analyte, for example, lead inside a sample, and then you do the process, okay, of the digestion and so on, the sample preparation process, and after that you analyze. After you have done the sample preparation process, okay, you know the exact amount actually. For example, it is 1 ppm. But after you do all the process of sample preparation to the sample, you have lost some of the analytes. For example, the reading now is not 1 ppm but 0.8 ppm, or it is much higher than the known concentration. For example, 1.2 ppm. But the acceptable criteria is between 80 to 120%, meaning that loss 20 or add more 20% is acceptable. But out of this range, the method is not relevant, not more suitable. Okay, meaning that the acceptable criteria for the recovery, okay, you spike non-concentration, for example, and then you do the process of the sample preparation, and then you analyze. For example, you have 1 ppm initially you put, and then you analyze, you have only 0.7 ppm, so that the loss of sample is quite large, okay, outside of the range of 80 to 120%. So that the recovery is have the acceptable criteria, which is between 80 to 120 to accept the method of sample preparation and so on. So how analyte can lose during the sample preparation? During the absorption, all right, metal ion can absorb on the glass surface of the instrument, of the apparatus, and also organic compounds can absorb on plastic containers and so on. That is the reason why the analyte lost during the sample preparation process. Also can lose due to the decomposition, okay, because organic compounds can decompose by oxidation. All right, then we have the analysis. This is the part that I told you we need to teach the instrument. Okay, we need to do the calibration. Okay, all right, and then also in the reading process we need to do blank. The blank is just the blank test must be carried out in the parallel with the determination. Okay, for example, in your sample preparation you use distilled water, okay, to dilute all the sample up to the mark, okay, during your digestion and preparation and so on. So in the analysis, when you run the instrument, you need to have the distilled water itself without adding anything, okay, as the blank, so that the instrument will know the background of the of the sample that you have analyzed using the instrument. The background are the distilled water. So the instrument will subtract the background concentration from the distilled water. Sometimes your distilled water also has some metals inside, okay, also absorb some radiation from the light source in the AS. So you need to analyze the reagent blank during the analysis, so that the instrument know this is not totally from your analyte. The absorption also come from the distilled water. Okay, so distilled water is used as the blank to subtract. Okay, and then preparation of digested sample. Okay, the reagents, the standard. Okay, this is the known concentration or the stock or internal elements that you use at known concentration. You need to prepare the series of calibration, right, to teach the instrument. And then we have the calibration plot. Okay. This is how we can prepare the standard. Okay. With an exact concentration. For example, you have 1,000 ppm, but you need to do only for 10 ppm, for example, right? For ICP-MS and ICP-OES, the calibration is much more easier. You only need to put the, for example, the range of calibration for nickel is from 0 to 0.25 ppm, for example, ppb, for example. You only need to prepare the highest concentration, 0.25, and then you put an instrument. The instrument will do the M1, V1, M2, V2, which is the dilution, okay, for other concentration of a standard calibration. Meaning that all these expensive instrument, ICP-OES and ICP-MS, we don't need to do one by one the concentration of calibration. We do the highest concentration and the instrument will dilute it and do the calibration for us. That's why we pay so much for this instrument, okay? All right, and then calibration graph, okay? This is the linear graph, okay? Y equal to mx plus b. What is b? B is the intercept. All right, the R square, okay, the goodness to the fit. Okay, the perfect one is 1. Okay, the R square. Okay, how your calibration concentration rely on the straight line of the linear equation or linear graph, right? Normally, it's not very good. Rely on all the line, all of the analyzed concentration. Sorry, all of the calibration solution that have been analyzed not rely on the straight line normally, right? But if it is rely on the straight line, you are very perfect in preparing the solution. R square equal to 1. But the perfect one is the minimum one acceptable is 0.995. Right? If you got 0.999, which is most of the standard concentration rely on the straight line, that is very good. Right? You prepare you prepare all the solution with the exact concentration, very good. Right? So acceptable is 0.995. Okay. That's why I told you the instrument only can we are accept all the reading from the instrument if it's rely between your calibration plot. For example, you have done 5 concentration, 1, 2, 3, 4, 5 ppm. If the sample analyzed, if the sample that has been analyzed, the instrument read about 6 ppm, it is already outside of your calibration plot. So this is not so accurate. You need to dilute the sample so that it rely between your calibration plot. Okay, this is calibration curve. It's very, very bad, right? The R square is 0.53. Okay, and then this one is good. The R square is 0.995. So sometimes it happens because of the outlier. Okay, actually it's quite good, but sometimes it's becoming bad because one of the concentration is outlier. So we repeat this concentration, and then if the repetition of the analysis of your prepared concentration back to the line, it will fix your R square value. Okay, determining unknown values from calibration curve. Okay, we have prepared. And then if the unknown sample rely between this concentration, okay, for example here, the instrument will read according to the calibration plot. So refer to the concentration here. All right, that is how we teach the instrument. Okay, sometimes we also have this is external standard, the normal calibration. We prepare the series of concentration together with reagent blank, QC, and also sample. Okay, QC is any concentration that we need to test our instrument. So that, for example, we have prepared 1 to 5 ppm. Okay, and then we want to test the instrument. Does the instrument really know the concentration after we teach the instrument? So we prepare one more, for example, 2.5 ppm. And then we read using the instrument. So if the instrument read, okay, perfectly 2.5, so the instrument is our good student because we teach them with this concentration and the instrument know how to read. Good student instrument, right? So that's why we need to have QC, the quality control. Okay, reagent blank. Okay, the blank is what is the metrics in all the calibration or sample that we have used. For example, distilled water. Okay, DW, distilled water, or double distilled water, DDW, or distilled deionized water, and so whatsoever, ultra pure water, UW. So use this water for the blank. If you put acid in all the sample for the digestion, put also the similar amount of acid into the blank, so that the instrument know this is the background. If there are some metals inside the acid or inside the ultra pure water, this is a background. Okay, this is not from the sample. Understood, guys? Please thumbs up. I feel that I'm talking alone here. If you have questions, just directly ask me. Okay. So this is the external standard, we call that. We prepared a series of standard solution and we analyze that is external standard. And then we have also the internal standard. Sorry, which one is the internal standard? The rest of the notes you have to read by yourself. Okay, I just point out all the important thing that you have to know. Yes, this one is standard addition. Okay, the standard or identical of analyte, the standard that we know the concentration, right? It's known quantity of the sample. It's suitable when the composition of the sample are known or too complex. This one, the standard addition, meaning that the previous one, we prepare all the standard, right, using the distilled water and whatsoever. For now, we call the second calibration method is we call as standard addition calibration. So how to do? Instead of we use the distilled water, okay, to prepare all the standard, now we use the sample itself. For example, you have the seawater sample, okay? Use the seawater sample to prepare the standard calibration. Hello, Dato'. So we prepare all the standards, okay, similar with the external standard, but now we use the sample itself to dilute all the standards instead of distilled water or ultra pure water and so on. Okay, how? So after we calculate how much the standards we need to prepare to put in the volumetric flask, okay, and then we need to dilute up to the mark, right? Up to the mark of the volumetric flask. Instead of using all the distilled water or ultra pure water, we use the sample itself. X is the sample. Okay. Prepare 0 ppm, so all the sample is here, not including standard. X plus 10 sample plus 10 ppm of the standard solution. X plus 20 ppm sample plus 20 ppm of the standards, and so on. Up, for example, you have 1, 2, 3, 4, 5. Okay, 0, 10, 20, 50, and 100. A series of 5 concentration, right? So you have sample plus the standards in all the standard solution, and also you have blank here. Okay. So when you read, the instrument will detect not from 0 here as all the external calibration. Let me show you again how the graph of normal calibration, right? If you prepare all the standard solution, okay, from a 0 up to what is the highest concentration? For example, this one is 8 ppm. Okay. Okay, guys. The important things for calibration plot is you must start the concentration at 0 ppm. Okay. So the absorption is 0. The concentration also 0. This is normal calibration. Okay, 0. But for the standard addition, because we use the sample itself instead of distilled water, now when you prepare the plot, it is not starting from 0. It is starting from some value here on the absorption. Can somebody tell me why? It is not from 0. For the external calibration, preparing the standard solution using the distilled water, it is start from 0 here. But for for the standard addition, we prepare the standard concentration mixed with the sample itself. The absorption not start from 0. It start from some value here. Why? Can somebody tell me? Please try. Please, we have several minutes more because I want to move to the assignments briefing.
Maybe because already have a bit analyzed already.
Yes, yeah, thank you so much. Because in the sample that we use, remember we use sample to mix with all the standards. There are some analyte already inside the sample. So the 0 ppm, for example, what happened to my... All right, so the 0 is now not 0, not really 0, because inside the sample itself, we have the analyte, X plus 0 ppm, okay? Meaning that only sample, of course, in the sample already have some analyte, okay? For example, this is how we prepare. We have this in all solution, we have a similar amount of sample. The different are only the standard solution, 0, 1, 2, 3, 4, 5 ppm, right? And then we put solvent to dilute it up to the mark, okay? So, I told you to prepare the standard addition, we need to use the sample instead of distilled water, right? But not for all, amount of sample that we need to dilute up to the mark. We need to set, okay, how many, okay, how many milliliter, or yes, in this case, milliliter of sample that we need to put. For example, in all calibration solution for the standard addition, we put 20 ml. So similar in all, okay, in all series, okay, 0, 10, 20, 50, we put how much? 20 ml of sample. Similar in all volumetric flask. And then the different are the amount of standard. Okay, for example, lead. We put lead standard here from 0, 2 ppm, this one 4, 6 ppm. We have one more 8 ppm. Okay, but the amount of sample that we put are all similar, 20 ml. Okay, 20 ml. And then to dilute it up to the mark of the volumetric flask, okay, we put the distilled water as well. Okay, we have the distilled water have no effect in this, right? But when the plot start here, okay, it is not due to the distilled water and so on. It is due to the analyte inside the sample itself. 0 is not really 0 because 0 is only 0 for standard solution. We don't put any standard solution here, right? Okay, and then the analyte the reading, the absorption here is due to the analyte inside the sample. And then we analyze another series of standard addition solution. We have here, and here. So now instead of we run the sample previously using the external calibration. After we done all the calibration, then we run the sample, right? And then the instrument we read within the calibration plot. And now we don't need to do this for standard addition. How to know the concentration of the analyte inside the sample? Just extrapolate it. Extrapolate from the point with the straight line. Okay. Extrapolate, and then you put extra also for the x-axis, and then you read what is the intercept here. What is it? It is negative, right? But just ignore the negative. Ignore the negative. For example, 0.04. Negative 0.04 is the intercept. So the concentration of the analyte inside the sample is 0.04 ppm, for example. Right? That is standard addition. We put a known and similar volume of sample inside all the calibration solution, put standards, okay, and then dilute up to the mark and run itself. No need to do the reading after we run the calibration, just extrapolate. And then we know the concentration based on this. All right, understood. If you understand, please thumbs up. We have two types of calibration, right? The normal one, the external calibration, just prepare the series of non-concentration, analyze it, and then run the sample, and then we refer to the plot. But for the standard addition, okay, because we put the sample inside the solution already, just extrapolate and we know the concentration. Right? Easy, right, guys? The standard addition. Do some revision, read again the notes of this, right? So this is extrapolate. All right, we have done all the spectroscopy part. The thing that you need to do is read the notes and watch my lecture video again in the YouTube. For today's class also, I will put in the e-learning. I record the video. Okay, now I would like to brief a little bit on the assignment, group assignment. How many students we have in this class? 73, right? Am I correct?
Hello, doctor. I'm not sure, but I think it's about 70.
What? You think what?
I think it's about 70.
Okay, let me check the official one.
Because in the e-learning got a lot about it.
Yes. Okay, we have 73.
73.
Yes, I can give you the list. Okay. Now, we need to form a group with actually the minimum number of person in a group should be 5. But now we have 73.
Doctor, I will suggest maybe 10 groups. So every group
Yes.
is 7 person. And then got 3 groups is 8 person.
No, because okay, let me brief to you the what we call the assignment method first. Okay, how to do assignment. It's very fun to do this assignment. All right, the assignment called as the different thinking hat jigsaw group for the sampling and sample preservation technique. Right, you have a case study. A chemical waste was dumped into a river, causing a water, soil, and air pollution. Meaning that the chemical produce, formation of volatile gas that have contribute to the air pollution as well. So an officer from environmental department, fire department, department of chemistry, department of fisheries, because some fish also died there, and local residents have to discuss to investigate the case. Assume that you are in the group of those pupils, plan the sampling and sample preservation to investigate the case. Identify what sample you should take, which standard method you should prefer, how to preserve the sample, how to store the sample, how you should analyze the sample. Okay. This is your group. As I told you, need to have a group of 5. Which is you can have the role, and you can rotate the role. Environmental officer, fire department, which is from hazmat. Hazmat is what? Hazardous material unit of fire department. And department of chemistry officer, and department of fisheries officer, and a local residents. Okay. In my class, in physical class, I will give the cap. So you will wear the cap of different roles. Okay. And then this is your main group. Okay. After you have identified all the role in the group, and then the second group need to discuss. Okay. The second group is you all the role in the initial group, your main group. For the fire department officers, of hazmat officers, all from all group will need together. All the fishery departments officer from all group need to be together, and local residents need together discuss what they need for the sample for the sampling and sample preservation. Okay. For the fisheries that we need to take the fish sample. We need to do this. Okay. For local residents, okay, this is our concern. You need to take this sample, this type of sample to analyze. Okay, we are local residents. We are very worried about our healthcare and so on. For the fire department, okay, hazmat material. Okay, we need to take, for example, only water sample because it is crucial in this part, the pollution or whatsoever. You need to discuss, and then after that, you back to your main group, the initial group. Okay. According to what you have prepared on based on the rule, that similar rule from all group, okay, you need to discuss. This is what have been discussed. So as the black hat is what? Black hat, for example, black hat or Department of Chemistry officer. I think this sample should be taken, and this is the sample preservation that we need to do, and so on. After your discussion between all roles in the group, you come up with the a form of either mind map, a table, or you can say you can do the video is better. Okay, any type of submission of the sampling and sample preservation planning is okay for me, right? Your mind map, table, point, poster, and so on. Video also can. And then include your group photo during the discussion inside the initial group and the role group. Also include the photo of discussion there, and then submit the planning. Okay, this is the rubric for the assignment. Okay, you have the understanding 20%, organization of the written planning 10, quality of sampling methodology related to the case 25, general chemistry terminologies and theories 25, interest level 10, timeliness, okay, 10 meaning that you submit on time, right? So that is the assignment that you need to do. So understand about the assignment. If you have question, please ask me. I will put the slides of this assignment instruction into the e-learning. Okay. And what you need to do now is form a group of 5. Form a group of 5 person. Okay. My advice is your group must be mixed with not only your, your colleague, okay, your close friends, okay, but mixed with all. Okay. 11 times 5, 3 times 6. So how many group do we have?
14
Okay.
group.
How many?
14
group.
group. 14.
14 group, right? Okay. So some group may have 6 person. It's okay. Meaning that the extra person will do the same role. You just choose the role, meaning that one of the role in the group will have 2 person. Okay, just up to your group to discuss that. You have you need to have the group leader also for all group for the submission and so on. I will show you the example of the assignment submission. Do you want to see that?
Yes, Doctor.
All right. Let me see. Let me find where it. Need to find it first. So wait for a while. Okay, let me find first. Okay, now we have one. And this example of their submission. Okay. But you know, this one got not so much marks, right? Because it's very simple. Okay. I should show another one. All right, this is another one, quite good. Okay. Okay, they have all the photos of their discussion as well. Let's see another one. Oh, this one is quite good. Together with a video as well. Okay. Wow. Complete the researcher search. Okay, and so they have video submitted to me. Okay, let us see the video. You want to watch the video for a while? Let me. Okay, let us watch.
Had jigsaw group activity. So Michael and a very good day, doctor. We are from group 8 and we'll be discussing different thinking head jigsaw group activity. Our group consists of Adam, Afif, Miza, Shafiq, and me, Sam. Sam, that is me, will be the environment officer. Afif is the chemistry department. Miza is local resident. Adam is fishery department. And lastly, Shafiq is fire department. So 5 of us.
Okay, let us watch the video.
Our approach we start by this when lastly.
We must define our problem first. For our case, the sample is fish, the metric is flesh.
Test method for determination of lead.
To preserve the sample, we can acidify with 2 ml of concentrated HNO3 per liter of water to prevent the loss of metals by precipitation, absorption, and/or ice. We can store it in polyethylene bottles at a low temperature at 4 degrees.
For analysis, how should we analyze the sample? For that, taking photos, discussion group photos from our presentation today.
Right.
Thank you.
So, how was it, guys? Really cool, right? Okay, I hope better from all of you. Okay, the group formation is up to you. I will give the name list to Eng. Okay, Eng. I will give the name list to you.
Okay, doctor.
Eng, can you text me just to know which one is your WhatsApp number? Text me for a while. And then
Already text.
already text. All right, good.
Yeah, just now. So that's
Yeah,
what
we'll
the
send-
group, we will form ourselves or what?
Yes, you form the group for yourself.
Okay, I will suggest later I will give a Google
Yes.
the link, and then you press inside, and then
Yeah.
later inside the group, and then just.
If I agree, yes, you gave me the link for the Google Google what? Google what we call that?
Google form.
Google
no,
Form. No, Google Form.
Sheet,
Google
Google
Docs. The sheet, right?
Google Sheet
Google
of
document.
docs. Yeah.
Google Docs. All right. And then if I agree, I will tell you that I agree with the grouping. And then we just proceed with the assignments. Okay?
Okay, doctor.
All right. So I think that's all for today. I will put in the e-learning all the instrument, all the assignment instruction in the slide. I will put in PDF. And then you will do your grouping, and then you can start your assignment. Okay. Choose your own time when and where to discuss. It is on your part. Okay. Okay, everyone. Do you have any question? We'll end our class now.